In the last class, we have seen Green's functions in quantum field theory and the singularities that are arising from the Green's function and how to overcome those singularities. So the first method what we have defined was that to go above the singularity. Okay, so that there is no singularity in the contour. So redefining the contour such that when you go above the singularity, there is no singularity inside the contour. Now today we will see the second method. So if you have to specify a contour like this each time, then it's not convenient to integrate the complex integral. So there is another way to tackle this problem, and that is, instead of going around the contour, we just try to move the singularity by a tiny bit. For example, in the retarded Green's function GR, right? So in x-axis I have real omega, y-axis I have imaginary omega. So in the retarded case, I have minus omega and plus omega k. These are the two poles, omega k and minus omega k. So this is the same if I just slightly move the singularity below the real axis. So this is the original singularity. I am going to slightly move the singularity below the real axis. Okay, so I have shifted. There is a tiny shift. So this tiny shift will not affect the answer. Similarly, in advanced Green's function, we have to move the singularity above. And in the case of Feynman's Green's function, I have to move one singularity above and move another singularity below, so that I don't have to change my contour. I only have to shift the singularity. So this can be achieved by a method which is known as epsilon prescription. Okay, so GR of x prime is equal to integral d4k by 2 pi to the power 4. So I have minus I by, so initially it is omega square plus omega k square. So this was what we defined yesterday, but here there is a shift in omega, so I have to incorporate the shift in omega. Okay, so it is omega plus I epsilon whole square plus omega k square as usual. So this is the shift, and this method is called as epsilon prescription. Okay, and there is e raised to I k x minus x prime as usual. Okay, so for t greater than 0, that is for t having positive values and infinitesimal. Why I am writing infinitesimal? Because it's a tiny shift, a tiny piece that I am looking at. So infinitesimal. Then omega plus I epsilon whole square plus omega k square is equal to 0. This will be the poles. Now let me see how the poles are getting shifted. If this is the case, then omega is equal to plus or minus omega k minus I epsilon. If the epsilon is not there, then it's the ordinary case, omega is equal to plus or minus omega k. But here I have plus or minus omega k minus I epsilon. So we always do the integral with the same contour. We don't change the contour, but we slightly change the pole to minus omega plus I epsilon whole square. So we just try to shift the pole. So we can see that by adding such a tiny piece to omega, the relation between the poles also becomes shifted. I mean, the solution is also getting shifted. And here there is a minus. So this minus indicates that the pole is shifted to the lower half of the plane. Okay. So this is for GR, retarded case. So we have already seen that we have to shift the poles to the lower half of the plane. So this negative sign denotes the minus sign. Okay, this minus sign indicates that the pole is shifted to lower half of the plane. Okay. Similarly, for advanced Green's function, we have to subtract I epsilon from omega. So here I have added I epsilon. So this is for retarded function, retarded Green's function. For advanced Green's function, I'm not writing the other terms. Okay, I have to write minus omega minus I epsilon whole square plus omega square. I have to subtract I epsilon from omega, and both the singularities will move up to the upper half of the plane. Minus omega minus I epsilon whole square plus omega k square is equal to 0. Then I will get omega is equal to plus or minus omega k plus I epsilon. So this plus indicates that both the singularities, that is plus or minus omega k, will move up. So in general, I can write G R or A of x comma x prime is equal to integral d4k by 2 pi to the power 4 minus I by omega plus or minus I epsilon. Okay, if it is retarded function, it will be plus. If it is advanced, it will be minus. Okay, so for both I can write plus or minus. Okay, in general, this is a general form, plus omega k square e raised to I k dot x minus x prime. So this is for retarded and advanced function. And for the Feynman's Green's function, you can use the same trick. Okay, but in this case, the epsilon addition or subtraction is outside the square. So here you have done it inside. Okay, so there is a whole square here. So this addition is actually inside this bracket. Okay, and there is a whole square that is outside. But in the case of Feynman's function, I have to write d4k by 2 pi to the power 4 minus I by k square plus m square minus I epsilon. Okay, so in this case, it is outside the square, and you have e raised to I k x minus x prime as it is. So when you solve for omega, you get the situation where one pole will move up and the other will move down. So that is for Feynman function. From the contour integration point of view, the precise shape of the contour is not important. It only matters what the singularity that it encloses. So yesterday we have seen, if you have two poles, then you just go above, right? And just close the contour. In that case, so from the contour integration point of view, the precise shape of the contour is not important. What only matters is that what singularity it encloses. So in this case, it is not enclosing the singularity. Singularity is actually outside. It is not enclosing. So that is only matters when it comes to contour integration. So far, as it encloses the singularity, it is the same. Since I changed the singularity location only by epsilon, at the end I can take epsilon tending to 0, and then again the two stories will be the same. That is, the contour changing will be equal to shifting the poles. This happens when epsilon tends to 0. Okay. So we are almost at the end of concluding the free field theory. So far what we have seen was free field theory. There were no interactions. It's a free field theory. So before going to interactions, let's discuss some remarks. First one, G plus and GR have many applications, okay, especially in condensed matter. And the Feynman function GF plays an important role in the interactions, which is the next topic. So we'll see the role of the Feynman function in the next topic, but they have many applications, especially in condensed matter. And so far we have seen the correlation function of 2 points, okay, just the x and x prime. But in principle we can consider more general correlation functions, okay. And also we have seen this in the vacuum state, phi of x, phi of x prime, something like this, right? So here you have used vacuum state. So it's not always required to be vacuum state. You can also use another state, for example psi, right? So this is only a limited case what we have seen, and in general you can have more correlation functions, okay, in any arbitrary state psi. So I can represent it by psi, phi of x1, phi of x2, phi of x3, etc. up to phi of xn psi. Okay, so this is the general correlation functions. So this is something like endpoint function. So you said 2-point correlation, 3-point correlation. Now this is endpoint correlation. And also we have seen that it's not necessary to be a vacuum state. You can also use any arbitrary state psi. Okay. So the general state psi can be built from A and A dagger. Any state psi can be built from A dagger. Phi can also be written in terms of A and A dagger, that we have seen, right? Phi can also be written in terms of A and A dagger. Therefore, this general correlation function, we know everything about the general correlation function, and in this theory everything is computable because psi can be built from A and A dagger, and we already know that phi can be written in terms of A and A dagger, which means that in this theory everything is computable. We know all the functions. If you are considering the endpoint function in vacuum, then it is interesting to note that we can factorize it into sum of product of two 2-point correlation function. Okay, so instead of an arbitrary state psi, if I am using the vacuum, then I have phi of x1, phi of x2, phi of x3, etc. up to phi of xn. Okay, then my claim is that I can factorize it into sums of product of 2-point function. Okay, why this is because all these phi will have a and a dagger. It's a function of a and a dagger, and this correlation will survive when you have the correct ordering of a and a dagger. So a and a dagger has to be paired. If a dagger creates anything, then it has to be annihilated by a later. So that means all the a and a dagger has to be paired. Therefore, the endpoint function has to be reduced to different 2-point function. For example, let's take the simplest case. Okay, I'll use 4-point function. For example, I'll use a 4-point function. 4-point function means phi of x1, phi of x2, phi of x3, phi of x4. So this is a 4-point correlation function. So here I'll try to convince you that when a dagger from this phi of x4 acts on the vacuum, it excites the state and it can be annihilated from, okay, so when a dagger that is present in phi of x4, so each function phi will have a and a dagger, right? So this has a dagger, this has a dagger. All the phi will have a and a dagger because it's a combination of creation and annihilation operator. So when the a dagger from the phi of x4 acts on the vacuum, it excites the state and it can be annihilated by an annihilation operator a from any of these phi, right? Therefore, I have to write down all the possible pairings. So this will be G plus x1, x2, x3, x4. This is one possibility. Otherwise, or in the sense I have to use plus, or G plus x1, x4 and G plus x2, x3, or G plus x1, x3, x2, x2, x4, right? x2, x4. Okay, so therefore in free theory, any point function, any endpoint function in the vacuum reduced to 2-point function. So any endpoint function I can reduce to 2-point functions. So these are all 2-point functions. So if you know the 2-point function, okay, how to solve the 2-point function, then you know everything, because any endpoint function can be reduced to a 2-point function. So once you know how to compute a 2-point function, then you know everything. Now, in addition to phi, we can also consider more sophisticated composite operators. Composite operators. So far we have seen expectation of only phi, right? Phi of x1, phi of x2, phi of x3 up to phi of xn. But instead of phi, you can also have phi square, phi cube, okay? And why not Hamiltonian density or T mu nu? So what are composite operators? Instead of phi, I can use composite operators, say phi square of x, phi cube of x, right? Otherwise I can use the Hamiltonian density. Otherwise I can use the stress tensor T mu nu. I can use all of them. Okay, all of these involve some product of phi. So here phi square means what? Phi of x multiplied by phi of x. So all these composite operators have phi in some or the other form, right? In some of the other product form or its canonical momentum. For example, here you have pi also, phi dot also there. So pi, either you have some product of phi or its canonical momentum. So most of the times these operators are not well defined, because when you try to multiply them at the same point we arrive at singularity. So such kind of singular behavior is common in quantum field theory, and one of the most important aim of quantum field theory is to find different ways to renormalize the divergent quantities in a physically sensible way. How can you eliminate the singularity? That is the main aim of quantum field theory, one of the main aim of quantum field theory. So far we have discussed the simplest free field theory, that is the theory of free scalar particles with spin 0, that establishes a connection between the field and the particle. Now let's discuss about interaction. So here we have interaction between the fields. So that also we have to take into consideration. It's not a free field, right? So there is one more potential that will be appearing from the interaction. So previously we have considered the Lagrangian to be minus half del mu phi minus half m square phi square. Now we have to make it interacting by adding some higher order powers. Okay, so I have to add higher order powers. So next higher order power will be phi cube, right? So I have to add something. Okay, so Lagrangian is T minus V. So if I am adding something to the potential, for example V prime, then it will be T minus V prime. That's why I am writing minus here. Okay, so when I say I am adding to the potential, and which will get subtracted from the kinetic energy. Okay, fine. So I have to add the next higher order term. So next higher order term will be phi cube, but mostly we avoid odd powers of phi in the Lagrangian density, because when you have an odd pair, it does not have a definite sign. For example, if you have phi is negative, then phi cube is negative. If phi is positive, then phi cube is positive. So it doesn't have a definite sign. But if you consider the even powers, it will have a definite sign. So phi cube does not have a definite sign, implies that it does not have a well defined energy. There is no well defined energy. So the energy can go arbitrarily negative. It can go negative to how much? Up to negative infinity also it can go. Therefore, the simplest interacting theory with well defined energy will be phi raised to 4. Odd powers are always ignored or avoided. Okay, so now I have to add lambda by 4 factorial phi to the power 4. Okay, so here lambda characterizes the importance of the interaction. Okay, so lambda characterizes the importance of the interaction, and it is called coupling constant. It is called coupling constant, and it characterizes the importance of the interaction. Okay, So the total Lagrangian is now the Lagrangian of a free particle subtracted by lambda by 4 factorial 5 raised to 4. So this is the interaction potential. Interaction potential. Now let's follow the general quantization procedure by writing the classical general solutions for the equation of motion and then promote each solution to operators. So that's the way that we have followed. So let's follow the same way. So the equation of motion will be del square phi minus m square phi. Then here 4 and 4 will get cancelled. Then I have lambda by 6 phi cube equal to 0. So this is the equation of motion. So now we can see that we have a non-linear equation. Here there is phi, here there is phi, but here there is phi cube, which means this is non-linear equation. So earlier when there was no interaction, it was a linear equation. Now it is a non-linear differential equation. And we don't know how to solve it. Okay, so non-linear equation cannot be solved exactly. But we can always approximate some solution. So heuristically we can imagine lambda to be very small and find an approximate solution. So one of the main tasks of particle physics is to figure out the interactions from the experiment. For example, the Large Hadron Collider LHC, okay, which is situated at the European Organization for Nuclear Research, which is known as CERN, situated in Geneva. It operates the world's largest particle physics laboratory where protons are collided together. And the whole purpose is to figure out the interaction between the elementary particles. Experimentally, the most powerful way to probe the interaction between particles is scattering. So starting from the Rutherford experiment, for more than 100 years, scattering is the universal approach to probe the particles to figure out its substructure and also its interactions. So basic idea of scattering is to collide a bunch of particles and examine the outcome. So from here the interactions can be deduced, and it has always been very successful. And in condensed matter also you have neutron scattering, X-ray scattering, right? So you use the X-rays to shine on your sample and you get the X-ray diffraction, etc. So from the point of view of quantum mechanics, one of the important object in scattering theory is the S matrix. Okay. From the point of view of quantum mechanics, one of the important object in scattering theory is the S matrix. S matrix is one of the key observable for scattering. In order to define the S matrix, we need a mathematical idealization. Okay, what do you mean by idealization? You don't have it in reality, but you are describing an ideal case. That is, at time t is equal to minus infinity, you have to prepare the initial state as localized wave packets that are infinitely far apart. So before colliding, so what you are saying, you are considering scattering. So when you want to do some scattering experiment, you have to prepare the initial state. So the initial state we are considering at t is equal to minus infinity, and final state will be at t is equal to plus infinity. And interaction will happen in between. Okay, this is before scattering, t is equal to minus infinity. After scattering, it is plus infinity, and the interaction happens in between these two. So at t is equal to minus infinity, we have to prepare the initial state as localized wave packet that are infinitely far apart. Okay, so initially the particles are far apart, and you have to aim them in such a way that you prepare their initial momentum so that they come together at some point, and then they will scatter and interact with each other, and the final product will go away from each other, and at the end they are again far apart, right? So initially the states are far apart, and you have to aim them in such a way that you have to prepare their initial momentum so that they come together at some point, and then they will scatter and interact with each other, and the final product will go away from each other at the end, and they are again far apart. That is at t is equal to plus infinity. So here final particles are also infinitely far apart. Okay, so as t tends to plus or minus infinity, the particles are far away. Okay, so at t is equal to plus or minus infinity, we can neglect interactions. So this is important, as we can identify each particle. When they are all together, it is not easy to discuss their properties, right? So in between, all the particles will be colliding with each other and scattering. At that time, it's very difficult to discuss their properties. Okay, this is very important, because to find out their properties, the particle has to be far away. So initial and final states are collection of free particles, and this plays a key role, as we cannot solve the kinds of interaction theory exactly. But now we can predict it with some accuracy with this kind of initial and final state. So let's denote the collection of momentum of the initial particles. Collection of momentum of initial particles to be alpha. So alpha is a collection of momentum of initial particles. So let's say that there are k number of particles, initial particles. Then there are p1, p2, p3, pk. Pk momentas will be there, and alpha is the collection of the momentum of initial particles. So this also characterizes the initial state. So I can also represent it by state alpha. Okay, this characterizes the initial state. And similarly, you can also have for final particles, let it be beta. So beta is equal to, I am representing p1 prime. So this is the momenta of the final particle. So p1 prime, p2 prime, etc. up to pn prime. So here you can see initially there were k number of particles, but after the scattering there are n number of particles. Okay, so the initial and final number of particles don't have to be the same. So you might have seen the interactions in particle physics, right? So one particle actually can decay into two particles, and two particles can come together and form one particle. So that can happen. So number of particles don't have to be the same before and after scattering. So that is not necessary. If alpha is the initial state and beta is the final state, then you can define the scattering process as alpha going to beta. Okay, so you start with a bunch of particles at time t equal to minus infinity, and then at t is equal to plus infinity you observe some other particles with different momentum, and then we try to understand this transition from alpha to beta. So from here you can get differential scattering cross section, differential scattering cross section, and things like that. Okay, but you can get anything, differential scattering cross section, etc., things like that. But alpha and beta are the fundamental in quantum field theory. Okay, they form the basis. So I can write beta, okay, and then an evolution operator, okay, which I am representing by u minus infinity to plus infinity, then acting on alpha. So u is evolution operator of the quantum system. Okay, and this is Schrodinger picture. This is in Schrodinger picture, but what we need Heisenberg picture, right? Schrodinger, this is Schrodinger picture. What I want is Heisenberg picture. So in Heisenberg picture, I can write it as beta plus infinity and alpha minus infinity. Okay, so the state itself is defined at plus infinity, and this state itself is defined at minus infinity. Okay, so here you can see this is of a matrix form. This evolution operator is a matrix form. Here you have alpha and beta. So correspondingly, if alpha equal to 1 and beta equal to 1, then you have the matrix element 1 1, right? U 1 1. Then if alpha is equal to 1 and beta is equal to 2, then you will have u 1 2. So this is a matrix. This evolution operator is a matrix. And what is the dimension of the matrix? It can be infinity, right? Because alpha can take any number, beta can take any number. So this matrix can have any number of elements. Therefore, I represent it by the matrix S beta alpha. So this is a metric element S beta alpha. When beta takes some value, alpha takes some value, then you get that particular element in the matrix, not the exact matrix itself, but the element in the matrix. For example, S12, right? S21, etc. So these are the elements of the scattering matrix. So varying alpha and beta over the all possible values forms a very big matrix. It can be an infinite matrix, and that matrix is called the scattering matrix or S matrix. Okay, so any choice of alpha and beta will give you one metric element. So basically S beta alpha is the metric element of this evolution operator. Now let's see the properties of S matrix. Properties of S matrix. So when there is no interaction, which means there is no scattering, then alpha will be equal to beta. Yeah, so if there is no scattering or no interaction, then alpha will be equal to beta, first property says that the scattering matrix will be an identity matrix, okay, which I can represent by delta alpha beta, because alpha equal to beta means no interaction. So it will be identity matrix. And when the interaction is weak, okay, so you have some interaction but it is weak, then I can represent by, I have to add those interactions plus I t, okay. So this t is also a matrix which includes the interaction effects. So we expect the energy momentum conservation due to translational symmetry, okay. And therefore, in terms of the component of rotation, I can write S beta alpha is equal to, so this is a component from this S matrix. Similarly, identity matrix will also have 1 0 0 1. This is in 2 dimension, but if the dimension is different, then you can have zeros and ones. So I can in general represent by delta beta alpha plus I t beta alpha. Due to momentum conservation, the sum of initial momentum must be equal to the sum of final momentum, and therefore the interaction term must contain a delta function connecting the total initial momentum and the total final momentum, okay. So the interaction term must contain a delta function. So I have to define this. We know this also, we can find out I is a complex number, right, root of minus 1. And what is t beta alpha? That is the question. How do you find this t beta alpha? So we know that for any interaction to happen, you should have a momentum conservation. That is, sum of the initial momentum must be equal to the sum of the final momentum. Then this interaction term must contain a delta function connecting the total initial momentum and the final momentum. Therefore, for convenience, I write I t beta alpha is equal to I 2 pi to the power 4 delta of p alpha minus p beta and m alpha beta, okay. So this interaction term will be of this form. This Dirac delta must be present for conservation of momentum. And all these terms are trivial terms, okay. So this is a constant and this delta function is incorporated so that conservation of momentum is taken care of. So these are all trivial terms, and the non-trivial term is the scattering amplitude. So m alpha beta is the scattering amplitude, okay. This is the non-trivial term. So that is the first property, okay. You can write S matrix in the form identity matrix plus IT, okay, where the second term IT is the interaction term, and the interaction term can be represented in this way with the Dirac delta and the scattering amplitude. Now, second property. The S matrix is the matrix of the unitary evolution operator, right? We have already seen that there is a unitary evolution operator u minus infinity plus infinity, and S matrix is the matrix of this unitary evolution operator. So this implies that the matrix S is also a unitary matrix. That is the second property. Now the third property. For any symmetry of the Hamiltonian, if you have any unitary operator that commutes with the Hamiltonian, right? For example, let lambda be the unitary operator. Okay, let lambda be a unitary operator and it commutes with the Hamiltonian. Okay. So for any symmetry of the Hamiltonian, if you have any unitary operator that commutes with the Hamiltonian, then the interactions are generated by the unitary operators. It will satisfy S lambda beta lambda alpha is equal to S beta alpha. That is, if you operate lambda on beta and lambda on alpha, the scattering matrix is same as that of the scattering matrix without this unitary operator, right? So when you act initial and final state with the unitary operator lambda, then the matrix should be the same, because lambda commutes with U and S is the metric element of U. Okay, so for any symmetry of the Hamiltonian, that is, you have any unitary operator that commutes with the Hamiltonian, then it will satisfy S lambda beta lambda alpha is equal to S beta alpha. Okay, and the final properties. The final property says that the M alpha beta, right, the scattering amplitude can be obtained from the time ordered correlation function. Okay, so time ordering means you order the operator according to their time. So bigger the time, the operator that should come first. So this is the key object if you want to calculate the scattering amplitude. So the last property says that M alpha beta, or the scattering amplitude, can be obtained from time ordered correlation function. What is time ordered correlation function? I have a state, then T, time ordering of phi of x1 up to phi of xn and omega. So why I am representing omega here? Because the vacuum state, you use this state for free theory, but here now you are discussing about the interacting theory. So this state omega is the vacuum state for interacting theory. Okay, so the fourth property says that the scattering amplitude can be obtained from time ordered correlation function, which is given by this. So what do you mean by time ordering? It means that you order the operator according to their time. Okay, so phi of x1, then phi of x2, etc. That is based on their time. So bigger the time, the operator will come first, which means that if I am writing phi of x1 first and then phi of x2, then the bigger time is phi of x1. So bigger the time, it will come first. Okay, then the next smaller will come, then the next smaller, etc. Okay, so this is the key object if you want to calculate the scattering amplitude m alpha beta. So once you get m alpha beta, you can substitute it here and you get the interaction, total interaction. Okay, so for today we'll stop here. In the next class, we will discuss how to solve the nonlinear equations generally, and we will also start with the path integral approach. Okay, so for today we'll stop here.